Hi there! In this video, we will learn how to use the 3 standard timers inside CODESYS. After that, we will start a simple project to use timers to control a belt conveyor. Okay, let's start the video and create a new project. Let's write a simple program. Assume that we want to control a belt conveyor by a normally open push button. Based on the program, we want this output to turn on or off whenever we activate or deactivate the push button. The timer is a PLC instruction measuring the amount of time elapsed following an event. Let's use an on-delay timer between the contact and coil to see how it can be added and used. Its instruction name is TON or TON. As you can see, we must define some parameters before insertion of the timer. First, each timer needs a variable to work correctly. Although any name can be written here, I prefer to use the default name and hit the Enter key. As you know, when a new variable is entered, CODESYS opens this window to specify its properties. Note that the selected data type of the new variable is TON. This type of data is used to store necessary information appropriated for on-delay timers. For example, the predefined time parameter must be entered at the second input. The time can be entered in a millisecond, second, minutes, hour, and so on, like these examples. Note that we must use the letter T plus hashtag symbol before the desired time to indicate that the entered value is a time. On the other side, a variable must be specified to store and display the elapsed time since the rising edge at the first input. Note that its data type must be time. Alright, I have inserted one on-delay timer with these two variables between my contact and coil. Now let's test the program to see its performance. As you can see, this variable, whose data type is TON, includes 4 parts. Now, let's start the simulation and use the start contact to activate the coil. Later, I will connect them to this equipment inside the Factory IO. Well, when I press Ctrl plus F7 keys on my keyboard to activate the state of a contact, the program enables the output after 5 seconds. Note that whenever I disable the start contact, the timer will be disabled immediately and the output will be off. Well, to see more details about timers, let's use the Help window. Well, there are three types of timers. The on-delay timer has already been tested. This diagram displays its performance. Whenever the timer is activated, it starts timing, and after the predefined time, the timer will activate its output, and whenever the timer is deactivated, its output will be deactivated immediately. The second standard timer is an off-delay timer, or just TOF. It is called an off-delay timer because its output is turned off after a delay. This diagram displays how it works. Whenever the timer is activated, its output will be activated immediately, and whenever the timer is deactivated, its output will be deactivated after a delay. The final one of the three standard timers is called the pulse timer, or TP. It is a very useful timer to generate a pulse of a specific length. When its first input changes from 0 to 1, in other words, receives a rising edge, it will generate a pulse at its output. Note that it won't be sensitive to new rising edges when it's in timing mode. Now let's test the off-delay and pulse timers. First, let me add an off-delay timer from the right list. As you can see, like the on-delay timer, the inserted off-delay timer needs a variable to work correctly, and its data type is TOF. Similarly, let me use a pulse timer inside the program. But there isn't any pulse timer besides the on-off delay timers. So let's go to the general list and add a general box. Then I can select a pulse timer by writing TP. Note that the timer uses another data type, TP, to store its inputs and outputs state. Now let's test the program. Okay, this window says the application changed since the last download. It means the current program is different from the previous one, which has been downloaded into my PLC. The window is asking us, what do we want to do? The first choice is log in with online change. That means that if the PLC is in a running mode, its program will be updated quickly without stopping the PLC. So at the next scan cycle, the new program will be executed. The second choice, log in with download, means that the PLC will be put into the stop mode and all its variables will be reinitialized. Also, we can log in without any change. This is not very useful because the program that we will have will not be the one that is currently executing on the PLC. So let's log in with download option. Note that the last checkbox is really important because if we take this box, we will also overwrite the boot project. It's the project that will be run at the start time and the power on instance of the PLC. Often we will need to enable this box. Let's continue. Now if I enable this contact, because of the on-delay timer, the belt conveyor will be on after 5 seconds, and because of the pulse timer, the warning light will remain on just for 15 seconds. Now if I disable the start contact, because of the off delay timer, the first output will be off after 10 seconds. Alright, these three standard timers have been tested. Let me define a simple project. I want when the start push button is pressed, my program turns on the alarm siren and warning light. The alarm siren will be on just for 5 seconds. After that, the emitter and belt conveyor must be turned on to move boxes. When the stop push button is pressed, the emitter will be off immediately and the belt conveyor remains on for 10 seconds to move the remaining boxes. After that, the program turns off the belt conveyor and the warning light. Note that if the emergency button is pressed, the start push button won't work. Finally, the emergency button can be used to stop the belt conveyor immediately. First, try to write an appropriate program for this simple project by yourself. I explained this program before. It can be used to turn on the belt conveyor with a delay, but it isn't practical because the operator needs to press and hold the push button. So let me write a program that uses these two push buttons to save a start-stop request on a bit of memory of the PLC. Okay, this program uses a set coil to hold a start requests on this variable receiving from the start push button. Similarly, the stop push button with a reset coil can be used to clear the start request. Well, if you simulate this program, it will work correctly, but if you connect it to the push buttons, it won't work, because the stop push button is normally closed. Therefore, this contact will be activated and it is closed in normal condition. In consequence, the reset coil will be activated and reset the start request in normal condition. To solve this problem, I need to use a normally closed contact instead of a normally open one inside the program. Note that the reset coil has been used after the set coil. So if both push buttons are pressed, Although the first line will store the start request, the second line will clear it. In consequence, we won't have any start requests. Let's continue. Usually, before starting any device, some safety conditions must be checked. For example, if the stop push button is pressed, the start command must not function. Likewise, if the emergency button is pressed because of some emergency conditions. Note that, like the stop push button, the emergency button is normally closed too. So, although I have used two normally open contacts inside the program, they will be activated in normal conditions, and I will only need to press the start push button to save the start request on this variable. To simulate the program, it's better to change the initial value of the emergency variable to 1 or true. Likewise, let me initialize the stop PB variable to 1 or true. Note that the AND logic can be used to check all necessary conditions before starting a device. Inside the second network, I can use parallel contacts to stop devices based on different conditions. In this project, the emergency button can clear the start request too. Okay, I wrote this program to store the start requests on this variable. Now let's write a program to turn on the alarm siren. I want to turn on the alarm siren for 5 seconds before the belt conveyor. So let's use a pulse timer. I can directly write TP or click here and find a pulse timer. As you can see, there is a red line under this variable because it is not defined yet. So let me write it again and use the auto declare window to specify its data type. Now let's write a program to turn on the warning light. After each start request, it must be turned on and remain on as long as the belt conveyor is running. Let's continue. The belt conveyor must be turned on after 5 seconds, so an on-delay timer must be used before the belt conveyor coil inside the program. As you can see, the selected new variable name is TON1 because I used an on-delay timer with ton 0 whose data type was ton. Note that the timer was removed, so I can use its variable ton 0 for the new on-delay timer. Let's set the predefined time to 5 seconds because the belt conveyor should start its work after the alarm siren. Similarly, let me use this variable whose data type is time for the ET output. Okay, based on the current program, after each start request, the alarm siren is turned on just during the first 5 seconds. The warning light is turned on and the belt conveyor starts running after 5 seconds. Remember, when the start request is removed, in other words, after each stop request, the belt conveyor must be turned off after a delay to move all of the remaining boxes. So let's use 2 off delay timers before the warning light and the belt conveyor. Note that when the belt conveyor is running, the warning light should be on too. I think 5 seconds is enough to move all of the remaining boxes completely. Okay, the emitter produces boxes inside the factory IO. It should be on when the belt conveyor is running 5 seconds after each start request, but after each stop request, it should be turned off immediately. So I can create a branch after the on-delay timer to turn the emitter on after 5 seconds, but turn it off immediately. Okay, it seems the program is completed, but if you test it, you will find a problem. Although both the emergency and the stop push buttons are used to stop the belt conveyor when an emergency condition happens, the belt conveyor must be stopped immediately. So let's use an emergency contact before the belt conveyor coil. If the emergency button is pressed, this contact is open, causing the belt conveyor to shut down immediately. Similarly, let's use an emergency contact before the emitter coil. Note that PLCs execute the whole program and then update all their outputs. Therefore, another way to consider an emergency condition is using an emergency contact with a reset coil at the end of the program to shut down the belt conveyor. Let's delete the last line because I have already considered the emergency conditions inside the previous network. Now I am going to link my program to Factory IO. Let's exit from the simulation mode. The next step is to specify which variables of the program should be shared with the Factory IO. Now let's run my controller, CODESYS control Win3. Now let's connect the controller to CODESYS and download the program. Here I write the device name and its password. The controller is connected to CODESYS successfully, so I can download and test the program. Now let's use Camtasia EX software to create and connect an OPC server to the controller. Its necessary settings were explained already. Now I need to define some tags inside Camtasia EX to connect to the program variables. Okay, let me define the first tag that can be read or write the state of the variable. I can select any name or the new tag, but I must be more careful when defining the address field. Just pay attention to the arrows. Alright, other variables can be defined similarly. Alright, I defined all the tags. Now let's click on the Quick Client icon. As you can see, the connection quality is good and the state of the two tags is 1 or true because their corresponding variables inside the controller are true. Now let's run Factory IO and design the system which I explained in the previous video. Note that by default forced mode is selected for the emitters and removers inside the Factory IO. I want to control the emitter with the program, so it's necessary to change its mode to normal. Now let me define which type of boxes I need. Well, let's continue to design a control box. The system is designed. Now let's connect the inserted equipment to define tags inside the OPC server. Remember that on the other side, these tags have been connected to my program variables. Okay, now I can control the system by the PLC program through the OPC server. Let's sort the windows to see the program networks, the system, and the OPC quick client window simultaneously. As you can see, if I press emergency button, I cannot use the start push button to store a start request. Let's inactivate the emergency button. Now I can use the start push button to run the system. Note that after a stop request, the belt conveyor and the warning light remain on for 5 seconds to move all of the remaining boxes. This box is not moved completely. Let's increase the time of the 2 off delay timers and test the program again. Alright, at this time the belt conveyor has moved all of the boxes. Let's test the emergency button. Note that the belt conveyor stops immediately when I press the emergency button. Okay, we finished this simple project. We will extend it later in the next video. In the next video, we will learn about the counter instructions. Thanks for watching this video. See you in the next one.